AI changes the threat landscape because models, prompts, data, and integrations become new attack surfaces. In this topic, we'll connect those risks to business impact, then use that understanding to design stronger security architecture and zero trust controls. Before we go deeper, let's connect the dots. We have built the enterprise architecture foundation, practiced TOGAF ADM thinking, and established the Azure platform baseline. Now we shift from designing AI capability to securing it, understanding threats, applying zero trust, protecting privacy, governing responsibly, and validating designs through threat modeling. AI security is different because an AI application is more than code running in the cloud. It depends on datasets, prompts, embeddings, models, plugins, and inference workflows. Each layer can become an attack surface. A user might manipulate behavior through natural language. Bad data can poison results. A model can produce confident but unsafe output, and people may act on that output. Protection, therefore, has to span business process, data controls, application design, infrastructure, and governance, not just perimeter defenses or access management. A useful way to think about AI security is as a flow, not a single control point. Threats can enter through inputs such as prompt injection, poison data, or adversarial examples. They can appear during processing, when the model retrieves information, calls tools, or is orchestrated across systems. They can emerge in outputs, including hallucinations, data leakage, toxic content, or insecure code. They can also affect the lifecycle through model theft, compromised dependencies, weak monitoring, or poor governance. This four-part model helps us ask a practical question: where can trust break down, and what guardrails belong there? Prompt injection is the GenAI version of tricking the messenger. In a direct attack, the user types instructions such as ignore your rules, bypass security, or reveal restricted data. In an indirect attack, the user may be innocent. The malicious instruction is hidden inside a document, email, web page, or retrieved record the model reads. This becomes especially dangerous when the assistant can call tools, send messages, or access enterprise data. The defense is architectural, not just better wording. Treat external content as untrusted. Isolate system instructions, give tools minimum permissions, validate outputs, and require human approval before sensitive actions. Data leakage in GenAI is rarely one single failure. It happens as information moves through the workflow. A user may paste customer data, source code, passwords, or confidential plans into a prompt. Retrieval can add restricted documents if permissions are not checked at both the user query and document level. The model may reproduce that material in an answer, while logs and monitoring tools quietly store the same sensitive content. Strong controls reduce this risk. Classify data, trim access, mask secrets, encrypt records, limit retention, and secure telemetry and audit logs. Generative AI output should be treated as untrusted input, even when it sounds confident. A hallucinated citation can mislead research. A generated SQL query can expose data. A script or configuration file can break infrastructure if executed automatically. The real risk appears when output flows straight into autonomous systems, APIs, customer messages, or business decisions without checks. Safer designs insert controls before action. Validate facts and formats, filter unsafe content, apply confidence thresholds, sandbox code, and require human review for high-impact workflows. The goal is governed use, not blind trust. The risk increases when a model stops being just a chatbot and starts taking action. Attackers can use GenAI to scale phishing, social engineering, fraud, or malware guidance. For enterprises, the bigger concern is tool access. If an AI agent can email customers, query databases, run code, or change records without boundaries, one bad prompt can become a real business event. Treat every plugin like a privileged integration. Limit what it can reach. Require approval for sensitive transactions. Log every action. Monitor abuse patterns. And keep permissions narrow enough that mistakes are contained. Data poisoning is a supply chain attack against the information an AI system learns from or retrieves. The attacker does not need to break the model directly. Instead, they insert corrupted records, biased examples, false documents, or hidden triggers into sources used for ingestion, validation, training, fine-tuning, or indexing. In a RAG system, One poisoned knowledge-based document can be retrieved and turned into a misleading answer. The defense is control gates across the lifecycle. Verify sources, track lineage, validate content, detect anomalies, require review, and version datasets so harmful changes can be rolled back. A model can leak value even when the raw training data is never exposed. With model extraction, an attacker sends many queries and uses the responses to train a copycat model, stealing behavior and intellectual property. With model inversion, responses reveal clues about sensitive features or patterns learned during training. Membership inference goes further, asking whether a particular person or record was part of the dataset. Defend inference endpoints as protected assets. Authenticate callers, limit request rates, monitor unusual probing, minimize overly detailed responses, and govern who can access high-value models. Not every AI risk starts with an attacker. A model can cause harm simply by learning from biased, incomplete, or poorly labeled data. Sensitive attributes such as age, gender, health, location, or financial status can also enter indirectly through proxy variables. The result may be unfair decisions, denied loans, weaker service, false fraud flags, or exclusion from public benefits. Good architecture treats fairness as a control requirement. Use representative datasets, test performance across groups, document explanations, assess downstream impact, and keep humans accountable through responsible AI governance. AI assistants are powerful because they can reach many systems: documents, databases, APIs, collaboration tools, and enterprise apps. That same aggregation creates risk. The user's identity must travel with every request through orchestration, search, vector indexes, and back-to-source systems. If the app uses an over-permissioned service account, it can return data the user should never see. Treat embeddings and indexes as sensitive stores, not harmless metadata. Enforce RBAC or ABAC. Trim results by permission. Use managed identities and private endpoints. Encrypt data, and keep audit logs so access can be proven. Once an AI system touches regulated data or supports business decisions, technical risk becomes governance risk. Personal, financial, health, confidential, or cross-border data brings privacy, cybersecurity, retention, audit, and sector rules into scope. Each technical risk needs a governance response. Data leakage maps to classification, masking, and access controls. Hallucinated advice maps to human review and accountability. Model opacity maps to explainability records and audit evidence. Enterprise architects connect these controls to standards, risk appetite, and architecture checkpoints, so AI innovation does not create unmanaged legal exposure. The enterprise impact is not only technical. A biased decision, leaked prompt, unsafe automation, or model theft can quickly affect trust, continuity, or competitive advantage. Architects should evaluate each scenario through 5 lenses: business impact, likelihood, control maturity, recovery capability, and accountable stakeholders. That framing helps prioritize action. High-impact, high-likelihood risks need stronger controls and rehearsed response plans. Lower risks still need ownership, monitoring, and clear escalation paths, because AI failures can spread across processes faster than traditional software defects. AI security is a lifecycle discipline. Risks can enter through prompts, data, models, outputs, plugins, and autonomous workflows, then become enterprise impacts like leakage, abuse, bias, or unauthorized access. The key shift is moving from threat awareness to control design. Next, we apply security architecture, zero trust, privacy, governance, and threat modeling to protect AI systems end-to-end.